Hello class. In this section we introduce the idea of a function. Let's begin with the definition of a relation. A relation is any collection of ordered pairs of the form xy. For example, right here you see a collection of 5 ordered pairs. So you're seeing right here 4 different relations. Now we say y is a function of x to describe a relation where for any one x coordinate in the relation there is only one corresponding y coordinate. So we're going to look to determine which of these 4 relations here we can say y is a function of x. So let's look at the first relation. Notice that there's a repeat x coordinate and they correspond to different y coordinates. This is a violation of the description here when we say y is a function of x. In order to say that y is a function of x, we need it to be true that for any one x coordinate, so 3 in this case, there is only one corresponding y coordinate. Yet for 3 we have 2 different corresponding y coordinates, and therefore we cannot say that y is a function of x. I'll highlight the reason that is the issue. Okay, let's look at the next relationship. If you don't see any x coordinates repeated there, then we really don't have any risk of violating that condition. So this one here, we are safe to say that y is a function of x. Every single x coordinate, 0 for example, has only one y coordinate that goes with it. Let's look at the next relation. Scanning the x coordinates, I do see that there are 2 that are repeated, 2 and 2, and they do have different y coordinates that correspond to them, 3 and 9. So we would say y is not a function of x. And let's look at the last one. In this last case, we have no repeat x's here in this column, so we are going to be safe to say that y is a function of x. Okay, let's look at the next line that's written up here. We say x is a function of y to describe a relation where for any one y coordinate in the relation there is only one corresponding x coordinate. So the thinking that we do here is the exact same thinking we've already done, except we switch the x and y in our thinking. In order to determine whether x is a function of y, you look to the y's, look for any repeats. If you see any repeats, then we have definite risk for violating that second condition. But here notice that there are no repeated y's in this first relation. So we can say that x is a function of y. In the next relation, scan the y coordinates. I don't see any repeats here. That means every single y coordinate can only have at most one x coordinate that gets associated with it. So this is going to be another case where we say x is a function of y. In our third relation, scan the y coordinates. I see 2 3's, so going the other direction, we have a 0 associated with the 3, and we also have a 2. So one y coordinate, that y coordinate's 3, but 2 different x coordinates. Say x is not a function of y. And in the last relation, look for any repeats in the y, and there's several of them. I see a bunch of 5's. This direction you can see that one y coordinate actually corresponds to 3 different x coordinates. But again, that's a violation of this statement that's made right here. X is not a function of y. In one case here, we saw that x was a function of y and y was a function of x. So one x leads to one y, and one y leads to one x. In other cases, we only had a function in one direction. Like in this case here, we would say that x is a function of y, but we could not say y is a function of x. Similar in this case over here. We could say y is a function of x, but we could not say that x is a function of y. And then in this third relation right here, we did not have a function in either direction. Okay, moving forward to the next slide. Any equation involving 2 variables implies a relation. Which relation is the set of all ordered pairs which satisfy the equation? So when you write an equation like this that has x's and y's, every single point that satisfies this equation is in that relation. For each equation below, determine whether that equation represents y as a function of x and or whether that equation represents x as a function of y. So I'm going to do this actually a few different ways. If I were to take this equation here and try to solve it for y, we would get 3y is equal to 6 minus 2x. And then divide everything by 3 next, and you get y isolated. So you divide 6 by 3, we get 2, and divide 2 by 3, we get 2/3. Let's see if y is a function of x. That means we're going to start with any x coordinate that you want. For example, put in a 3 in for x, and then calculate what y would be. Well, you do 2/3 of 3, which is 2, and then subtract that from 2, you get 0. The question you should be wondering is, was it possible to get 2 different answers here when I substituted 3 for x? Well, if you do 2/3 of a number, you get a single number. And then when you subtract that single number from 2, you still get a single number. I'm not seeing any step in my calculation here that would produce multiple answers. suggesting that no matter what I change x to, this calculation will yield only one result. So that reasoning allows me to conclude that y is a function of x. Let's do this with all 4 equations first before I do the other consideration. If I take this second equation and try to solve it for y, let me add the 1 over, so we got y squared equals 1 plus x. But then when you take a square root, you have 2 possible answers, plus or minus the square root of 1 plus x. So if I start with an x coordinate and calculate the y, for example, let's plug in 8. And when x is 8, you do get a square root of 9, which is 3, but then plus minus. So you actually get 2 different y's that correspond to the same x. This violates the condition for y to be a function of x, because one x led to multiple y's. So we would say in this case that y is not a function of x. Third equation, all we have to do to isolate the y is add the 1 to the other side, and then ask yourself, if you replace x with a number, is it possible to get multiple y coordinates back? And the answer is no in this case, because when you square a number, it becomes a single number. And then when you add 1 to that, it just stays a single number. If I start with x equals 3, for example, 3 squared is 9, plus 1 is 10. I don't get multiple answers here for y when I started with 3. Now it is true I could start with a different x and get the same y, but this is not violating the condition for y to be a function of x. So this is a case where one x will yield one y, so we get to say that y is a function of x. This last equation, add the 1 first over, we're trying to isolate the y, keep in mind. But then when you take a square root to get y isolated, again you have this plus minus situation. Make a table of points, you would see that we have some problems here. For example, if I plug in x equals 2, so you get a minus radical 5 and a positive radical 5 is 2 different y's that both correspond to the same x. So that violates the fact that y is a function of x. In other words, y is not a function of x in this case. So we've gone through and did the first consideration, whether or not we could say each equation represented a relation for which we could say y is a function of x. Now let's see whether the equations represent relations for which we could say x is a function of y. Now a good way to do that is take these equations and solve them for the other variable and try to solve it for x. So I'll begin by subtracting the 3y. So we have 2x equals 6 minus 3y, and then I'll divide both sides by 2. And then ask yourself the reverse direction. If I started with y coordinate, is it possible to yield multiple x coordinates? Every time you change y to a new number, you get a single number out of it. You can't plug in y equals 5, for example, and get multiple answers for x. So we do get to say that x is a function of y. Okay, let's take the second equation, which was y squared minus 1 is equal to x. And let's solve for x. Well, x is already isolated, so there isn't much to do there. But the question is, when I do a table of points, and I start with the y, plug in 5 for y. Well, when you plug in 5 for y, you're going to square it first, which is 25, and then minus 1, you get 24. Now, it's true that if you plug in negative 5, you will also get 24, but we're looking for whether a single y produces one or more x's in return. It seems like no matter what y I start with, when you square it, you're going to get a single number, and then when you subtract 1 from that, you're going to stay a single number. Any one y coordinate that I plug in here will only ever yield one x back. That means we get to say that x is a function of y. Let's look at the third equation. Y minus 1 is equal to x squared. Solve this for x, so I'm going to have to take a square root, which means I do have the plus minus radical y minus 1. If I start with certain y coordinates, like 2 for y, subtract 1, you get 1, square root of 1 is 1, and then you get plus or minus. So you actually get 2 different x coordinates that correspond to the same y coordinate. Therefore, we cannot say that x is a function of y. And let's look at the last one here. If I'm trying to solve for x, notice there's an x squared right there again. I'm going to have to take a square root, which means I'll have a plus or minus, and we have a y squared minus 1. This plus minus again is going to be the problem, because if you start with any y coordinate, like 7, but it would yield 2 different x coordinates because of the plus and minus. Therefore, x is not a function of y here either. Now, it's super easy when you're first doing this is to conflate the two definitions and be all confused. Y is a function of x means that x's produce unique y's. X is a function of y means that y's produce unique x's. You're going to have to do whatever it takes to keep those two straight in your thinking. Initially, they can be easily confused. All right, now for this next slide, we're going to suppose that y is a function of x. In such a case, the x coordinate is called the independent or input coordinate / variable. Another thing to call the x is just the argument. The y coordinate in these relations is called the dependent or the output coordinate or variable. These words input and independent make you think that you start with the x, you input the x, and then you do a calculation and that x produces a y. The y is outputted. So you start with the input and you produce the output. Notice that we are assuming that y is a function of x for this slide. But I could have also have said, suppose x is a function of y. in which case I'd say the y coordinates are the independent or input variables, and I would have said the x coordinates are the dependent or output variables. And because we're saying y is a function of x, we know that every input will yield a unique output. So these tables, the input of 0 yields a unique output of 0. Right? There's no 0, comma, something else other than 0. The input of 0.5 yields an output of 0.5. The input 3 yields the output 16. The input of 7 yields the output of -4. And the input of 1 yields the output of 9. Now, the set of all input coordinates of a functional relation is called the domain. And so the 5 numbers you see in this column here are said to be the domain of this function. So I'm going to put them in set notation, curly bracket, and I'm going to write them in order. So there's a half in there, the 0.5, there's a 1 in there, there's a 3 in there, and there's a 7. You don't have to write them in order. These 5 numbers are said to be the domain of this function. Now, all the outputs, the y coordinates in this case, are considered the range. For this second relation, so once again, we're thinking of x as the input variable and y as the output variables. All right, the domain, again, is all the inputs, in this case, all the x coordinates. And the range is the set of all the output coordinates. And some of them are repeated. The smallest is 2. And you don't need to write multiple times ones get repeated. There's a 5 in there 3 times and a 7. Right, there's only 3 possible numbers in the range, 2, 5, and 7. Another word for range, by the way, is called the codomain. Domain should always be associated with the input variable, and codomain or range should always be associated with the output variable. So everything would flip-flop if I went up here and said x is a function of y, and I gave you different tables to work with. I'd have to give you different tables in that case, because this table here, it's not true that x is a function of y. But if I did say up here that x was a function of y, and I gave you tables for which that was true, then the domain would be the y's, because they're considered the inputs now. And the range would be the x's. Right, so you really want to think that range and domain are connected to input and output. Do not make the mistake of always assuming x is domain and y is range. Suppose an equation represents y as a function of x. It is common to solve the equation for y and then to replace the y with the notation f parenthesis x parenthesis, which is read f of x. We're going to do this for the equation below. This is an equation we've already worked with on a previous slide. It does represent y as a function of x, and it's easy to see if you solve for y right away, which we did before. We had 3y is equal to 6 minus 2x, and then divide both sides by 3. And when you have isolated the y, it's common to replace that y with this notation, f of x equals 2 minus 2/3 of x. Now, the reason we are using the letter f is just to stand for the word function. But really, you could use any letter. You could say g of x. You can put a word there. You could say weight of x. But in general, we'll just say f to stand for function. So the f is called the name of the function. The input variable is what's in the parentheses. So when you see f of x, this is saying that there's a function that's going to input x coordinate and output something else. This whole side of the equation over here is called the rule of the function. It's the set of instructions, if you will, that tells you what to do with the input. And then when you put f of x together, or the rule all by itself because they're the same, these are two different symbols for the output. Right, so the x alone is the input, but f of x is considered the output. So if you were to make a coordinate, x would be the input, and you can write f of x as the output, and you would say, there's my point, x comma f of x. Or you could do something like this. X is the input, and the output is 2 minus 2/3 x. Or you can go more general. Right? All of these are saying the same thing. The thing that's occupying the second coordinate there all represent the same thing. To evaluate a function is to replace, or the word plug in, the input variable in the rule with a given number or expression, and then simplify when appropriate. This function right here is what we're referring to. So for that function, find f of 2. So we take our rule. If I change this x to a 2, then I change that x to a 2, and then I do this calculation. So we get 2 minus 2/3 of 2. And 2/3 of 2 is 4/3, and remove 4/3 from 2. Well, this 2 here is 6/3. Remove 4/3 from 6/3, and we get 2/3 as the final result. So the input was 2, and the output was 2/3. If I input -3, let's plug it in. So we do 2 minus 2/3 of -3. First I do this calculation. 2/3 of -3 is -2. And then do 2 minus -2, and that's going to give me 4. So the input was -3, and the output was 4. You could even plug in expressions. It doesn't have to be a number. If I say, hey, what's f of w? Then you would say 2 minus 2/3 of w. And that's about as far as we could take that, because I don't know what w is. You can plug in, like negative u. So this would be 2 minus 2/3 of negative u, which you could rewrite as 2 plus 2/3 of u. You can plug in z plus 1. So this would be 2 minus 2/3 of z plus 1. And I usually cross my z's when I'm handwriting them. Let's go ahead and distribute the negative 2/3 and just see what this simplifies to. So we have 2 minus 2/3 of z, and then minus another 2/3. And now I can combine this 2 and this negative 2/3. That's the same thing as 6/3 minus 2/3, that's 4/3. So in the end, I get 4/3 minus 2/3 of z. And here we have a negative f of x. So f of x, right, is the same thing as just that. But there's going to be a negative in front of all that. So we have the negative, I'm going to put some parentheses and then rewrite what f of x is. F of x is 2 minus 2/3 of x. We just do the negative of the rule. And then if you want to distribute the negative, it would read negative 2 plus 2/3 of x. All right, this is how you evaluate functions. You just replace the input variable with something else. Now, it should be pointed out that the symbol f of a, so when you see f of a all by itself, it represents the output that corresponds to the input a. In other words, there's a point at play here, a comma f of a. Another way of phrasing it is that f of a represents the result of plugging in a. So when I plugged in 2, input 2, output f of 2. Of course, f of 2 is 2/3, so I could also just say 2 comma 2/3 is one point in my functional relation here. Recall the following restrictions. If you ever have a fraction or division, like b divided by a or b over a like this, then this expression can only be possible if a is not 0. There is really no restriction on what the numerator can be, but the denominator, a, cannot be 0. So every time you see a fraction or you have division, the divisor or the denominator of the fraction cannot be 0. Also, if ever you have a radical, it's an even root, so like a square root or a fourth root or a sixth root, then the inside of the radical, the a, this is called the radicand. The radicand must be non-negative, meaning it has to be 0 or higher. Examine why that is real fast in case you've forgotten. If I say, hey, what's the square root of 9? You get the answer 3. If I say, what's the square root of 0? You get the answer of 0. But when I say, what's the square root of negative 9? We don't get a real number. We can use imaginary numbers and say 3i, but if we want to stay working with real numbers only, then we simply say that this is not real. In other words, we say it's not possible. And that's true for any even root. Not true for odd roots. Just as a quick reminder, right? If you do an odd root, like a cube root of 8, you get 2. Cube root of 0, you get 0. Cube root of negative 8, you can do. You get negative 2, right? Because negative 2 cubed is negative 8. So you can odd root positives, negatives, or 0. But you can only even root positives or 0. You can't even root negatives if you want to stay working with real numbers. So if ever you have an even root of something, that something must be bigger than or equal to 0. All right, so here are some functions given. M of x equals the square root of 2x minus 6. G of x is equal to x plus 7 all over x squared minus 3x. And P of x is equal to 2x cubed minus 5x. And we're expected to find the domain of each of these functions. Now, when we did domain up above, our function relationships were very few points. Just 5 points were in this one, and just 5 points were in this one. But typically, when you're working with an equation, like this equation right here represents infinitely many points in our relation. If I were to make a table of all the points that are satisfied by this equation, it would have infinitely many points in it. So it's very common to have an infinite set of points that's in the relation, not just a finite set like we saw with these tables. So here, when I'm talking about the domain of each of these functions of x, we're asking about, hey, what are the x's that can be plugged into this equation? So here we have a square root. This is an even root of 2x minus 6. So this function implies that the radicand, which is 2x minus 6, must be bigger or equal to 0. And I want to solve this for x. You could add the 6 and divide by 2, but I'm going to actually leave the 6 here and subtract the 2x over here, just to remind you that when you are working with an inequality like this and you divide both sides by negative, you need to flip the direction of the inequality. So the next step would be divide both sides by 2. And as soon as I multiply and or divide both sides of an inequality by a negative number, switch its direction. So this would translate into x must be bigger or equal to 3. That would have been really easy to get right away if you had just done this the easier way. Keep the 2x on the left side of the inequality and add the 6 to the other side and then divide by positive 2. Dividing by positive 2 does not change the direction. Now, be careful. You might think that these two expressions are different. They're written backwards of each other, but they're communicating the same thing. X must be bigger than or equal to 3. 3 must be less than or equal to x. If you're to shade your answers on a number line, x must be bigger than or equal to 3. So we would take 3, we'd put a solid circle there, and then we would shade on that direction. You could also put a bracket on there, if you recall, instead of a solid dot. And then don't forget interval notation. Interval notation, we would say x is an element of, and then whatever is shaded on the number line, which is 3 up to infinity. The shading starts at 3 and it goes up to infinity. we include the 3, so put a bracket on it, and we always put parentheses on infinity. This is called interval notation. This should be something you've seen before. We could simply say this as well, that the domain is equal to, you could just put the interval, 3 to infinity. This is our domain. I also want to show you a notation that the book uses. It does a set notation. It says the domain is all x's, and then it does a vertical line. That means such that, and then we just simply say such that x is bigger than or equal to 3. So here's another way of saying it too. Mathematical synonyms, if you will. All right, this next one has a denominator. And when you have denominators, you have to avoid 0. So we just say, okay, well, this function implies, I don't care about the numerator. All that matters is that the denominator, which is x squared minus 3x, is not 0. We're going to solve this by factoring. We're going to factor out an x. That leaves x minus 3. Can't be 0. And then we get 2 answers out of this. X can't be 0, and x can't be 3. This domain, if you were to put it on a number line, would have a hollow hole at 0 and a hollow hole at 3, but everything else would be okay. So when you do the domain, I'm just going to put D for domain, and I'm going to use interval notation here. We have 3 different separate pieces that are shaded. We need an interval for each piece. So it would go from negative infinity up to 0. The 0 gets a parentheses because 0 is not included. So we have another piece that's 0 to 3, and we have a third piece from 3 to infinity. And then the symbol that we want to put between these pieces to show that x could be anything from any of these intervals is to put the union sign between them all. So your domain is the union of these 3 intervals. Now it's a lot easier to just say what x can't be. So sometimes you'll just see a simple d colon and then say, hey, x can't be 0 or 3. And in this last case, notice there's no even roots and there's no denominators. In fact, you can cube anything. You can cube positives, negatives, or 0, fractions, it doesn't matter. You can multiply anything by 5, and you can subtract any 2 things. There's no restrictions here. Because there's no restrictions on x, we say x can be anything. So you would shade the entire number line. Or you can say that the domain is from negative infinity to infinity. Or another way to say this is that the domain is any real number. And so if you put the bold capital R, that stands for the real numbers. There are no restrictions. Our domain is all real numbers. This next slide is about combining 2 functions into one. 2 functions can be combined using the 4 basic operations. Consider the functions of x below. So we have h of x is 5 over x, and g of x is equal to 6x squared minus 3x. So when you see this first notation, g plus h of x, this is really just saying that you're going to be doing g of x, and you're going to add to that h of x. And you do this by simply taking the rule of g. So the rule of g is 6x squared minus 3x, and you add that to the rule of h, which is 5 over x. And then you look for any possible similar terms that you might combine. Here there are no similar terms, so we just stop. When I see h minus g of x, right, this just means to do h of x minus g of x. So we do the rule for h of x, which is 5 over x, and we subtract, and we do the rule for g of x, which is 6x squared minus 3x. Now be careful here, when you're subtracting the rule of g of x, you want to subtract all of the rule of g of x. So you should really put that in parentheses. So in the end, it's 5 over x minus 6x squared plus 3x after you distribute the negative. When you see g side by side with h like this, the default assumption is that we're talking about multiplication. So you want to think of this as g of x times h of x. So the rule of g of x, use parentheses here again, 6x squared minus 3x. We're going to multiply that by h of x, which was 5 over x. And we can distribute the 5 over x. We just do the 5 times 6x squared, and then divide all that by x. So we have 30x squared all over x. And then do the second part of the distribution. 5 times 3x is 15x, but then that's over an x. And then continue to simplify. Looks like we can cancel an x in the first fraction, so we just get 30x. And the second fraction, the x's cancel entirely, giving just 15. And then finally, this last one implies division. So when you see g over h of x, it just means do g of x divided by h of x. The g of x was our 6x squared minus 3x, and that's going to be divided by 5 over x. And then we have some invert and multiply to do here, right? If you divide by a fraction, you multiply by its reciprocal instead. So we're going to multiply by x over 5 instead, and then distribute that x over 5, and we're going to wind up getting 6x cubed over 5 minus 3x squared over 5. And this is where we're going to stop this one here.